Here's your content organized into structured, readable paragraphs, without skipping any words. For the first time in over 400 years, humanity might witness a supernova visible to the naked eye. No telescope, no filter, just a cosmic titan lighting up our skies. Its name is Betelgeuse, and while saying it 3 times won't summon anything spooky, it might just summon the brightest light show humanity has seen in over 4 centuries. This red supergiant is roughly 600 light-years away, and in recent years, it's been acting off, flaring, dimming, pulsing like a dying heart in the sky. What's behind this strange behavior? Is Betelgeuse really preparing for a spectacular finale? Today, we're diving headfirst into the mystery of one of the sky's most iconic stars, the one that is going to vanish from Orion's shoulder forever. Welcome to territory. This is your space. Betelgeuse is approximately 600 light-years away from Earth, meaning the light we see from it today left the star about 600 years ago. If Betelgeuse had already exploded in a supernova within the last 600 years, the light from that explosion would still be traveling towards us. In other words, it's possible that Betelgeuse has already exploded centuries ago, and we could see the explosion at any time, even tomorrow. When Betelgeuse does go supernova, it will be the brightest one ever seen by humans. So just how bright will it be? Will it be visible during the day? Will it pose any danger? And why do recent observations of Betelgeuse challenge our current understanding of stellar physics? Before we talk about what happens if Betelgeuse goes supernova, let's back up a little. While our Sun has been burning steady for about 4.6 billion years, Betelgeuse is a cosmic infant by comparison. Astronomers estimate it's only about 10 million years old. That means it's so fresh out of the stellar nursery that there hasn't even been enough time for solid rocky planets to form around it like Earth, and chances are they never will. Unlike our Sun, which is cruising through life with enough fuel to chill for another 5 billion years, Betelgeuse is burning out fast. Born with over 15 times the mass of our Sun, this stellar beast lived fast and large. From the moment it lit up, it started devouring its fuel like a cosmic glutton. Even before it ballooned into a red supergiant, it was already pumping out tens of thousands of times more energy than our Sun. Now, it's putting out over 100,000 times more power, an absolute furnace in the sky. And it's not just bright, it's unstable too, showing signs of exhaustion. When a red supergiant gets tired, only 2 outcomes remain. Let's start with the famous one, the supernova. As Betelgeuse runs out of fuel, its core begins fusing heavier elements, carbon, then oxygen, silicon, all the way to iron. But iron is the final stop. Fusing it doesn't release energy. It consumes it. When that happens, the core's furnace dies. Gravity, now no longer opposed by outward pressure, takes over. The core collapses in on itself. Now here's where the path splits. If Betelgeuse's mass is on the lower end of red supergiants, around 10 to 15 solar masses, then it's expected to collapse into a neutron star and go supernova in a massive explosion. That's the classical outcome for stars of that size. But if its mass is higher, closer to 20 solar masses, the gravitational collapse might be too intense for even neutrons to resist. In that case, Betelgeuse could collapse straight into a black hole with or without a visible explosion, no flash, no warning. The star simply vanishes. So, which fate awaits Betelgeuse? The truth is, we still don't know how massive Betelgeuse really is. And that's mainly because we haven't nailed down its exact distance from Earth, since even small differences in rotation, metallicity, or internal structure can tip the balance. This red supergiant is a cosmic coin toss, but if the odds fall in our favor, if that collapsing core hits just the right resistance, we're in for one of the most spectacular shows the night sky has seen in recorded history. To truly grasp the scale of what's coming, we need a little perspective. Our Sun has a luminosity, or power output, of 3.8 times 10 watts. However, A supernova observed in 2015 called a SASSN-15LH reached a peak luminosity of around 10 watts. The brightness would be the combined output of over 500 billion suns. But why didn't we see it from Earth? You ask. Well, ASASSN-15LH was located in another galaxy, Betelgeuse, however, is in our cosmic backyard. This proximity means Betelgeuse's supernova would be incredibly bright, potentially outshining even Sirius, the brightest star in our night sky, and it would likely remain visible for weeks. However, will it pose any danger to Earth? A supernova, occurring within a few tens of light-years from Earth, would have serious consequences, including harmful radiation exposure. The danger zone for these effects is estimated to be around 100 light-years. Fortunately, Betelgeuse is beyond this range, so we are safe from harm. For comparison, if a nearby star like Alpha Centauri just over 4 light-years away were to go supernova, it would shine as bright as the Moon and expose Earth to dangerous radiation. But Alpha Centauri is not massive enough to become a supernova, while there are other visible red giants that could potentially go supernova. Betelgeuse is currently the most intriguing, and that is why its recent activity has raised concerns among scientists. One fascinating aspect of Betelgeuse is its rotation. Recent measurements using the ALMA array of telescopes revealed that Betelgeuse rotates at a surprisingly fast rate, for a star of its size about once every 20 years. This means its surface spins at roughly 18,000 kilometers per hour or 5 kilometers per second, much faster than Earth's rotation. This rapid rotation is unusual for such a massive star and challenges our understanding of stellar physics. To measure a star's rotation, astronomers use the Doppler effect. Imagine an ambulance with its siren blaring approaching you. As it gets closer, the sound of the siren seems higher in pitch. This happens because the sound waves are compressed. As the ambulance moves toward you, once it passes and moves away, the sound waves are stretched out, making the pitch seem lower. This change in pitch due to movement is known as the Doppler shift. Similarly, for Betelgeuse, one half of the star's surface is moving towards us, while the other half moves away, creating a gradient of color shifts. By observing these shifts, scientists can determine the star's rotational speed. For Betelgeuse, this speed was found to be much higher than expected. One theory to explain this anomaly is stellar cannibalism, where Betelgeuse might have absorbed a companion star, gaining additional angular momentum in the process. Betelgeuse contains far more nitrogen in its outer atmosphere, which is a sign that its interior has been mixed recently, indicating that something happened to the star to spin it up. Putting these pieces together, astronomers recently performed a systematic and careful analysis of the intriguing possibility that Betelgeuse did not start off as a single star, but is instead the product of a collision. As the supergiant star aged, its atmosphere extended to the orbit of its companion. Scientists performed a simulation that revealed the companion star's gravity funneled that material onto itself, increasing its own mass. Eventually, the companion started swimming through so much material that this caused friction, slowing the companion and drawing it inward. Newer simulations now suggest that there might be a companion star involved, but that Betelgeuse didn't eat it up. Betelgeuse is classified as a variable star, displaying consistent cycles of brightness and dimming. These cycles, often compared to a heartbeat, happen over two separate time scales, one just over a year and another lasting approximately 6 years. A recent study utilized computer models to simulate the behavior of the red supergiant. The team of scientists explored various possibilities to explain the periodic pulsing of the star, including internal stellar activities and magnetic field fluctuations. However, their analysis consistently pointed towards the most plausible explanation: the presence of a companion star. The researchers fittingly dubbed this proposed companion Betel Buddy. Unfortunately, direct evidence for this scenario won't be easily apparent until Betelgeuse explodes into a supernova. So, when is Betelgeuse going to blow? Well, here's the good news and the bad. The truth is we can't pin down an exact date. Estimates put the explosion anywhere between 10,000 and 100,000 years from now. But here's the twist. Given how far away it is, and how light takes centuries to travel across space, it might have already happened. We could just be waiting for the flash to arrive. And that's a mystery that keeps us gazing up at the night sky with anticipation. Our star system appears to be a calm and stable place. Yes, there are times that the gas giants occasionally nudge a comet or asteroid out of their orbits, sometimes even sending them hurtling toward the direction of Earth. But overall, things have been generally stable. The Milky Way is estimated to contain around 200 to 400 billion stars, with the solar system orbiting through the galaxy. While the distances between stars are huge, in an ocean of these celestial fireballs, the chances of them coming close to each other cannot be ruled out. Around 75% of the stars in our galaxy are red dwarfs, typically having around 8% to 40% of the Sun's mass. The Milky Way itself spans a massive area stretching about 100,000 light-years across, with a central bulge roughly 5,000 to 8,000 light-years in radius. When calculating how often stars come close to our Sun, we consider factors like the density of stars in different parts of the galaxy, their orbits, and how fast they move relative to each other. Objects in the solar system. Scientists have studied space rocks for decades. So, comparing their typical trajectories with those of potential black holes could help distinguish between ordinary objects and primordial black holes. However, detecting a black hole's influence remains a challenge and would require some luck to spot a clear signal. For decades, modern astronomy has held to popular belief that the powerful jets responsible for the most energetic forms of radiation, gamma rays, originate from the distant cores of galaxies far beyond our reach. But what if these extraordinary forces were lurking closer to home? In the shadow of an ancient Mexican volcano, the High-Altitude Water Cherenkov Gamma Ray Observatory, or HAWC for short, has discovered something fascinating. Equipped with 300 water-filled tanks, this observatory captures gamma photons at staggering energies. And now its detectors have revealed something astonishing, something that challenges decades of scientific thought, something right in our cosmic backyard pointed directly at us. QASA, or S, rare supermassive black holes found at the center of galaxies pool in material and emit intense radiation and powerful jets. Scientists estimate that the last time Sagittarius asterisk, the supermassive black hole at the center of our Milky Way galaxy, became a quasar about 6 to 9 million years ago. Since then, it has gone quiet as it aged, but the remnants of that quasar ejection still present above and below the ecliptic of the spiral Milky Way disk. Today, the closest quasar to Earth resides in Markarian 231, a Type 1 Seyfert galaxy, located 581 million light-years from Earth. The jets launched by active quasars like Markarian 231 release electromagnetic radiation of extremely high energies. These energy particles, which are primarily high-energy protons and atomic nuclei, can reach incredibly high speeds when traveling through space, sometimes almost approaching the speed of light. Since Victor Hess discovered cosmic radiation in 1912, astronomers have believed that supernova remnants in our galaxy are responsible for accelerating these particles to the highest energies. However, a different picture comes from the latest data from the HAWC Observatory. The sources of radiation of extremely high energies in our galaxy turn out to be microquasars. These are compact binary systems consisting of a massive star and a black hole that consumes its matter, producing jets that can extend for hundreds of light years. Dozens of such microquasars have been discovered in our galaxy to date. But what the HAWC Observatory's detectors have captured are photons originating from a microquasar within our galaxy that possess energies tens of thousands of times greater than what is typically observed. The microquasar V4641 Sagittarius has been identified as the source of photons with energies reaching up to 200 electron volts. located in the Sagittarius constellation. It is approximately 20,000 light-years from Earth. A black hole with a mass around 6 times that of the Sun plays a central role in pulling in matter from a giant star that is 3 solar masses. These two objects orbit a shared center of mass, completing one revolution in just under 3 days. Interestingly, the jet produced by the V4641 system points toward our solar system. Consequently, the jet seems to move through space at a velocity exceeding light speed, in this case, up to 9 times the speed of light. In astrophysics, superluminal motion occurs when jets of material are ejected at speeds close to the speed of light and are pointed nearly directly at us. Because the jet's motion is directed toward the observer, the light from the jet reaches the observer in such a way that it appears to be moving faster than the speed of light. This is not a violation of physics, but a trick of perspective. This discovery demonstrates that, at a relatively close distance to Earth, the mechanisms responsible for jet formation and the generation of ultra-energetic photons are similar to those observed in quasars in distant galaxies. The only difference is that these activities in microquasars unfold over a much more relatable time-scale, days, as opposed to the hundreds of thousands or millions of years typically involved. This development means that astrophysicists can, for the first time, conduct detailed and nearly unobstructed observations of techniques vital to galaxy evolution. Thank you for watching this marathon. Let us know what you think in the comments below so that we know if we should create more marathons in the future. If you enjoyed this video, kindly consider becoming a member. It will help us create more new content so that we can keep bringing the latest news from the world of astronomy. And don't forget to subscribe, because this is your space. Along its surface, as centuries passed, these clouds condensed, giving birth to thousands of new stars. Our Sun was far from this event when the bubble began forming. But roughly 5 million years ago, it drifted into the bubble's interior during its journey around the galaxy. Now we reside within this expansive 1,000 light-year wide structure, observing active star formation on the bubble surface while the interior remains surprisingly empty. This discovery affirms a decades-old theory suggesting that supernovae can compress gas, creating fertile grounds for star birth. This led astronomers to think, if this phenomenon happened here, how widespread might these cosmic bubbles be across the galaxy? A group of astronomers has now charted the bubble, uncovering an unusual asymmetry in its shape and temperature distribution, as well as identifying a mysterious tunnel-like structure pointing toward the constellation Centaurus. Our local cosmic neighborhood just got a whole lot more intriguing. Imagine a fish trying to figure out the shape of its tank while staying right in the middle. It wouldn't be something very easy for the fish to do unless we give it human-like intellect and the right tools. Enter the right tool, the Max Planck Institute of Extraterrestrial Physics' powerful space-based X-ray telescope called EROSITA. One major advantage of EROSITA is where it operates. In space, Earth's atmosphere stretches surprisingly far, with a vast halo of hydrogen called the geocorona extending up to 100 times Earth's radius, which is more than 370,000 miles from the surface. EROSITA is mounted on the Space Observatory Station about 930,000 miles from Earth at a gravitationally stable point where the poles of Earth and the Sun balance. The X-ray Observatory is uniquely positioned as the first to capture X-ray images of the sky from completely beyond the reach of our planet's glowing geocorona. Using the telescope, the researchers found that the bubble is expanding more vertically away from the galactic plane rather than along the horizontal plane. This makes sense because vertical directions face less resistance compared to horizontal ones. The researchers found that the uneven temperature distribution in the bubble matched the supernova theory for its formation, suggesting that stars may have indeed been exploding in our region relatively recently, as close as a few million years ago. What we didn't know was the existence of an interstellar tunnel towards Centaurus, which carves a gap in the cooler interstellar medium. It stands out in stark relief thanks to the much improved sensitivity of EROSITA and a vastly different surveying strategy compared to ROSAT, says astrophysicist Michael Freiberg of the Max Planck Institute for Extraterrestrial Physics. We still don't know exactly what the tunnel leads to, but several intriguing objects lie in its path, such as the Gum Nebula, another neighboring bubble, and several molecular clouds. The team, however, suspects that the Centaurus tunnel in the local hot bubble may just be a part of a network of hot gas tunnels that bore their way between the cool gas of the interstellar medium between stars. It's possible that this tunnel could be part of a larger interconnected network of hot bubbles and cosmic tunnels that make up the galaxy, an idea first proposed in 1974, but which lacks significant evidence until now. Another interesting fact is that the Sun must have entered the local hot bubble a few million years ago, a short time compared to the age of the Sun, which is 4.6 billion years. Another scientist added, "It is purely coincidental that the Sun seems to occupy a relatively central position in the local hot bubble as we continuously move through the Milky Way. This new finding is exciting because now we might be on the verge of uncovering this network, which could provide valuable insights into the recent history and structure of our galaxy." What do you guys think? Comment below to let me know. Also, adding the link to the interactive version of the local hot bubbles 3D model in the video description in case you want to check it out. By the year 600 BCE, the pyramids of Giza had already stood for over 2,000 years, silently witnessing the rise of human civilization growing in rapid and diverse ways. It was during this time that our fascination with the stars began to turn into a study. The Babylonians recorded the movements of celestial bodies like the sun, moon, and planets, and developed a calendar that could predict lunar and solar eclipses. Meanwhile, the Greeks began to question the myths surrounding the world. They began to propose that the Earth was spherical based on observations like the shape of the Earth's shadow on the moon during eclipses. Astronomy was just beginning to take shape, and it was during this time that a star 2,600 light-years away erupted in a dramatic explosion. Now, 2,600 years later, we are going to witness that explosion in the night sky. Fascinating, isn't it? Imagine looking up at the night sky and noticing a bright new star where none had been before. This was the experience of Burid, the abbot of Eresburg in Germany over 800 years ago. When he observed a faint star that for a time shone with great light, the star he saw was T Coronae Borealis, a variable star in the constellation Corona Borealis, also known as the Northern Crown. A variable star is a star that appears to change brightness from Earth's perspective over time. T Coronae Borealis is 2,600 light-years from Earth, meaning that the events we observe today actually occurred 2,600 years ago. Now, during the prime of their lives, most stars are powered by nuclear fusion reactions deep inside their cores. However, Corona Borealis is well past its prime and is now a stellar remnant, known as a white dwarf. But Corona Borealis is not alone. It's a rare and fascinating binary star system, where it's locked with its stellar companion in a cosmic dance. The primary star is a white dwarf, a remnant of a once massive star that has exhausted its nuclear fuel and collapsed into a dense, Earth-sized object. This white dwarf, although seemingly quiet, harbors an immense gravitational pull, drawing in material from its companion star, a red giant. The red giant is a younger star, bloated and cool, shedding its outer layers as it nears the end of its life. This mass transfer is the critical piece of the puzzle in understanding why Corona Borealis is known as a recurrent nova. A recurrent nova. Does that mean it explodes over and over again? Yes, every 80 years, T Coronae Borealis puts on a show for us here on Earth. As the white dwarf draws off material from the red giant, it gradually accumulates on its surface over decades. This process leads to the buildup of a critical mass of hydrogen on the white dwarf's surface. Once enough hydrogen has been gathered, a powerful thermonuclear reaction ignites a runaway fusion event that causes the star to explode in a spectacular nova. When this happens, the energy released makes T Coronae Borealis shine 1,500 times brighter than usual, making it visible to the naked eye in the night sky. The last such explosion occurred in 1946, and as we pass the 80-year mark, the world eagerly anticipates the coming eruption. When T Coronae Borealis goes nova, the explosion releases an enormous amount of energy, blasting the accumulated material into space at high speeds. This creates a shell of gas that expands outward, and the system temporarily becomes one of the brightest objects in the sky. After the explosion subsides, the process starts all over again as the white dwarf continues to pull in material, repeating the cycle. But how are we so sure that we are going to witness it soon? T Coronae Borealis previous to eruptions in 1866 and 1946 exhibited similar patterns. Approximately a decade before each explosion, the star's brightness increased slightly, reaching what is known as a high state, followed by a brief dimming or dip about a year before the eruption. The star entered its high state in 2015, and the pre-eruption dip was detected in March 2023, which has put astronomers on alert. The reasons behind these patterns remain some of the intriguing mysteries surrounding T Coronae Borealis. But wait, once it explodes, we won't have much time. Yes, once Corona Borealis erupts, the peak brightness will be fleeting, lasting only a few hours. Within a week, the star will dim significantly, requiring binoculars to observe it. It's highly likely that an amateur astronomer will be the first to spot the eruption of the star and notify the professional astronomy community. These dedicated amateurs often monitor stars from their own observatories, filling crucial gaps in the observation of the night sky. During its peak brightness, the nova will be visible to the naked eye, though binoculars or a small telescope will offer a more detailed view. Despite not reaching the intensity of the brightest stars or planets, the nova will be a remarkable and memorable sight for sky watchers and amateur astronomers alike. And more than anything, it is kind of a once-in-a-lifetime cosmic event. So look up. Primordial black holes are thought to have formed shortly after the Big Bang, racing through space at incredible speeds, faster than a bullet. They could be passing through the solar system every decade, unseen, but potentially causing subtle disruptions. One popular theory even links these tiny black holes to the 1908 Tunguska event, where a massive explosion flattened over 2,000 kilometers of forest near the Tunguska River in Siberia. While popular theories suggest that the explosion was caused by the air burst of a meteoroid or a comet fragment entering Earth's atmosphere, no impact crater was found, and the explosion is estimated to have released energy equivalent to 10 to 15 megatons of TNT, about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Roughly 10 times the distance from the Sun to Pluto. Such close encounters are rare, occurring once every few 100,000 years. Even rarer are encounters within 500 astronomical units, which happen roughly once every billion years. So, it's highly unlikely that a passing star would disrupt the orbits of planets in our solar system. But while encounters with stars won't often cause direct issues for planets, they may disturb the Oort cloud, a distant region of icy bodies surrounding our solar system. We know that gravitational interactions between stars and the Oort cloud are always happening, but their effects may not be visible for millions of years. Over time, passing stars can send these icy objects hurtling toward the inner solar system, increasing the chance of cometary impacts. The last known star to pass close to the Sun was Scholz's star, which came near us about 70,000 years ago. However, new research suggests that a star may have come closer to Earth than the Voyager probes. Our solar system may have had an incredibly close encounter with another passing star. Not one, but two recent studies propose that a stellar flyby could account for the strange orbits of certain objects on the outskirts of our solar system, as well as some of the unusual moons orbiting nearby planets. This encounter, according to the research, was astonishingly close. A rogue star passed within 110 astronomical units of the Sun, meaning it came 110 times the distance from the Sun to Earth. To give some context, this star would have approached US even closer than the Voyager 1 probe, which, after being launched, is now 164 astronomical units away on its journey beyond the solar system. Given that the nearest star to us today, Proxima Centauri, is more than 4 light-years away, this was an incredibly close call. Such a near miss, the researchers suggest, would be necessary to explain the unusual and chaotic orbits of celestial objects located in the farthest regions of our solar system, beyond Neptune's orbit, to investigate whether a passing star's gravity could be responsible for the unusual orbits of some of the trans-Neptunian objects. The scientists ran over 3,000 computer simulations. Their findings not only confirmed the hypothesis, but revealed something fascinating. The simulation showed that this stellar encounter could explain 2 of the most peculiar trans-Neptunian objects, which have retrograde orbits, meaning they move in the opposite direction of the planets. It could also account for the distant dwarf planet Sedna, which orbits as far as 937 astronomical units from the Sun. A myth-going co-author and astrophysicist noted that the simulations pointed to a star slightly smaller than our Sun at about 0.8 solar masses passing within a little less than 4 times the distance from the Sun to Neptune. Interestingly, this event could also explain the strange moons in our solar system, such as Saturn's moon Phoebe, which has a retrograde and distant orbit. Similarly, Jupiter and Neptune host several irregular moons that could have been trans-Neptunian objects displaced by the gravitational influence of this stellar flyby. This could explain why the outer planets have 2 distinct types of moons: regular moons, which formed along with the planets and have stable, predictable orbits, and irregular moons, which have strange, or retrograde, that is, backward orbits and may have been captured from the outer solar system. If this star had a close encounter with our solar system billions of years ago, it could be a remarkable chapter that may have been overlooked. What do you guys think? Drop in your comments to let me know. Imagine floating through our cosmic neighborhood, where our sun and planets are cradled within an enormous, mysterious bubble, a swath of space that scientists call the local hot bubble. It's a sprawling region of low-density gas stretching hundreds of light-years in all directions, heated to millions of degrees. But how did this bizarre bubble come to be? Scientists believe that around 10 million years ago, multiple star explosions, or supernovae, occurred in this region. Research suggests that around 14 million years ago, powerful supernovae erupted, carving out a bubble of hot gas called the local bubble. Over time, this bubble expanded, sweeping up clouds of interstellar gas and dust.